Next topic, functional anatomy of the kidney. Multiple functions of the kidneys. Most people are familiar with one important function of the kidney is to rid the body of waste materials that are either ingested or produced by metabolism. The second function that is especially critical is to control the volume and electrolyte composition of the body fluids. Now if I get to write this. Volume, to control the volume and electrolyte composition of the body fluids. For water and virtually all electrolytes in the body, the balance between intake due to ingestion or metabolic production and output due to excretion or metabolic consumption is maintained largely by the kidneys. This regulatory function of the kidneys maintains the stable internal environment necessary for the cells to perform their various activities. The kidneys perform their most important functions by filtering the plasma, removing substances from the filtrate at variable rates depending on the needs of the body, and for ultimately the kidneys clear unwanted substances from the filtrate and therefore from the blood to excreting them in the urine by excreting them into the urine and while returning substances that are needed back to the blood. Although this chapter and the next few chapters focus mainly on the control of renal excretion of water, electrolytes, and metabolic waste products, the kidneys serve many important homeostatic functions, including the following, which are the excretion of metabolic waste products and foreign chemicals, we just mentioned, regulation of water and electrolyte balance, regulation of body fluid osmolality and electrolyte concentration, osmolality balance and electrolyte concentrations, and regulation of arterial pressure, regulation of acid base balance, regulation of erythrocyte production, secretion, metabolism, and excretion of hormones, and gluconeogenesis. Excretion of metabolic waste products, foreign chemicals, drugs, and hormones, and metabolites. The kidneys are the primary means for eliminating waste products of metabolism that are no longer needed by the body. These products include urea, which is created from the metabolism of amino acids, creatinine from the muscle creatine, and uric acid from nucleic acids, end products of hemoglobin breakdown such as bilirubin, and metabolites of various hormones. These waste products must be eliminated from the body as rapidly as they produce. The kidneys also eliminate most toxins and other foreign substances that are either produced by the body or ingested, such as pesticides, drugs, and food additives. Regulation of water and electrolyte balance. For maintenance of homeostasis, excretion of water and electrolyte must precisely match intake. If intake exceeds excretion, the amount of that substance in the body will increase. If intake is less than excretion, the amount of that substance in the body will decrease. Although temporary or cyclic imbalances of water and electrolyte may occur in various physiological and pathophysiological conditions associated with altered intake of or renal excretion, the maintenance of life depends on restoration of water and electrolyte balance. Restoration of water and electrolyte balance is an important one. Intake of water and many electrolytes is governed mainly by a person's eating and drinking habits, requiring the kidneys to adjust their excretion rates to match the intake of various substances. When we, look at this, response of the kidneys to a sudden tenfold increase in sodium intake from a low level of 3 equivalent per day to a high level of 300 equivalent per day. Within 2 to 3 days after raising the sodium intake, renal excretion also increased to about 300 equivalent per day, so that a balance between intake and output is rapidly re-established. However, during the 2-3 days of renal adaptation to the high sodium intake, there is a modest accumulation of sodium that raises extracellular fluid volume slightly and triggers hormonal changes and other compulsory and compensatory changes or responses that signal the kidneys to increase that sodium excretion. The capacity of the kidneys to alter sodium excretion as a response to change in sodium intake is enormous. Experimental studies have shown that in many people, sodium intake can be increased to 1500 mg per day, more than 10 times normal, or decreased to 10 mg per day, less than 1/10 normal, and relatively small changes in extracellular fluid volume or plasma sodium concentration. This phenomenon is true for water and for most other electrolytes such as chloride, potassium, calcium, hydrogen, magnesium, and phosphate ions. In the next few chapters, we discuss the specific mechanism that permit the kidneys to perform that amazing feat of homeostasis. So let's dive into this topic. First, regulation of arterial pressure. We just mentioned that function. Kidneys play a dominant role in long-term regulation of arterial pressure by excreting variable amounts of sodium and water. The kidneys also contribute to short-term arterial pressure regulation by secreting hormones and vasoactive factors or substances like renin that lead to the formation of vasoactive products like angiotensin II. So that is about regulation of arterial pressure. Then regulation of acid-base balance. The kidneys contribute to acid-base regulation along with the lungs and body fluid buffers by excreting acids and by regulating the body fluid buffer stores. The kidneys are the only means of eliminating from the body certain types of acids such as sulfuric acid and phosphoric acid generated by the metabolism of proteins. Regulation of erythrocyte production. The kidneys secrete erythropoietin, which stimulates the production of red blood cells by hematopoietic stem cells in the bone marrow. One important stimulus for erythropoiesis and the erythropoietin secretion by the kidneys is hypoxia. Hypoxia in the sense oxygen lower content. Then the kidneys normally account for almost all the erythropoietin secreted into the circulation. In people with severe kidney disease or who have had their kidneys removed and have been placed on hemodialysis, severe anemia develops as a result of decreased erythropoietin production. In regulation of 1,25 dihydrovitamin D3 production. The kidneys produce the active form of vitamin D, 1,25 dihydrovitamin D3. That is the calcitrol actually. So calcitrol by hydroxylating this vitamin at the number 1 position. Calcitrol is essential for normal calcium deposition in bone. And calcium reabsorption by the gastrointestinal tract. Calcitrol. Calcitriol actually. Calcitriol plays an important role in calcium and phosphate regulation. Then glucose synthesis. The kidney synthesize glucose from amino acids and other precursors during prolonged fasting, a process referred to as gluconeogenesis. The kidney's capacity to add glucose to the blood during prolonged periods of fasting rivals that of the liver. With chronic kidney disease or acute failure of the kidneys, these homeostatic functions are disrupted and severe abnormalities in the body fluid volumes and composition rightly occur. With complete renal failure, enough potassium, acids, fluids, and other substances accumulate in the body to cause death within a few days, unless clinical interventions such as hemodialysis are initiated to restore at least partially the body fluid and electrolyte balance. Physiological anatomy of the kidneys. General organization of the kidneys and urinary tract. The two kidneys lie in the posterior wall of the abdomen outside the peritoneal cavity. Each kidney of the adult human weighs about 150 grams and is about the size of a clenched fist. And 150 grams. The medial side of each kidney contains an indented region called the hilum, through which pass the renal artery and vein, lymphatics, nerve supply, and ureter, which carries the final urine from the kidney to the bladder. Hilum region, and it is stored until the bladder is emptied. This kidney is surrounded by a tough fibrous capsule that protects its delicate inner structures. If the kidney is bisected from top to bottom, the two major regions that can be visualized are the outer cortex and the inner medulla regions. The medulla is divided into 8 to 10 cone-shaped masses of tissues called renal pyramids. Kidney, ureter, bladder, urethra. Nephron, enlarged portion. You could see minor calyx, major calyx, papilla, renal cortex, renal pelvis, renal medulla, renal pyramid, capsule of kidney. Minor calyx, major calyx, papilla, renal cortex, renal pelvis, renal medulla, renal pyramid, capsule of kidney. These are the major portions of nephron. The base of each pyramid originates at the border between the cortex and medulla and terminates in the papilla, which projects into the space of the renal pelvis, a funnel-shaped continuation of the upper end of the ureter. The outer border of the pelvis is divided into open-ended pouches called major calyces and enter downward and divide into minor calyces, which collect urine from the tubules of each papilla. The walls of the calyces, pelvis, and ureter contain contractile elements that propel the urine towards the bladder, where urine is stored until it is emptied by micturition, as discussed later. So, the nephron is a functional unit of the kidney. Each kidney in the human contains about 8 lakh to 1 lakh nephrons, each capable of forming urine. The kidney cannot regenerate new nephrons. So, we try to learn about the human kidney section. You could see portions like interlobar arteries and veins, arcuate veins and arteries, then renal artery, renal vein, segmental arteries, and interlobar arteries and veins, and some other portions of this nephron. Arcuate artery, arcuate vein, afferent arteriole, juxtaglomerular apparatus, efferent arteriole, glomerulus, Bowman's capsule, proximal tubule, cortical collecting tubule, then loop of Henle, then collecting duct, some other portions like distal tubule and peritubular capillaries. So we just learned the kidney cannot regenerate new nephrons. Therefore, with renal injury, disease, or normal aging, there is a gradual decrease in nephron number. After age 40, the number of functioning nephrons usually decrease about 10% every 10 years. Thus, at age 80, many people have 40% lower functioning nephrons than they did at age 40. This loss is not life-threatening because adaptive changes will be taking place. In the remaining nephrons, allow them to excrete the proper amounts of water, electrolytes, and waste products. Each nephron contains a tuft of glomerular capillaries called glomerulus, through which large amounts of fluid are filtered from the blood, and a long tubule in which the filtered fluid is converted into urine and its way to the pelvis to the kidney. The glomerulus contains a network of branching and anastomosing glomerular capillaries that, compared with other capillaries, have high hydrostatic pressure. The glomerular capillaries are covered by epithelial cells, and total glomerulus is encased in Bowman capsule. Fluid filtered from the glomerular capillaries flows into Bowman's capsule and then into the proximal tubule, which lies in the cortex of the kidney. From the proximal tubule, fluid flows into the loop of Henle, which dips into the renal medulla. Proximal tubule is to a greater extent situated in the cortex. Okay. Loop of Henle is in the medulla. Loop of Henle in the medulla. Okay. Which dips into the renal medulla. Each loop consists of a descending in the sense is going into down. Ascending limb. These two limbs are there. The walls of the descending limb and the lower end of the ascending limb are very thin. The walls of the descending limb and the lower end of the ascending limb are very thin and therefore are called a thin segments of the loop of Henle. After ascending limb of the loop returns pathway back to the cortex, the wall becomes much thicker and it is referred to as the thick segment of ascending limb. After the ascending limb of the loop of Henle returns pathway back to the cortex, its wall becomes much thicker and it is referred to as thick segment of the ascending limb. At the end of the thick ascending limb is a short segment that has its wall a plaque of specialized epithelial cells known as macula densa. At the end of the thick ascending limb is a short segment that has its wall a plaque of specialized epithelial cells known as macula densa. Macula densa plays an important role in controlling nephron function. Beyond the macula densa, fluid enters the distal tubule, which, like the proximal tubule, lies in the renal cortex. This is followed by the connecting tubule and the cortical collecting tubule, which lead to the cortical collecting duct. Distal tubule, collecting tubule, cortical collecting tubule, cortical collecting duct. The initial parts of 8 to 10 cortical collecting ducts join to form a single leader collecting duct that runs downward into the medulla and become the medullary collecting duct. Medullary collecting duct. The collecting duct merge to form the progressively larger ducts that eventually empty into the renal pelvis through the tips of the renal papilla. So when we try to learn about the basic tubular segments of the nephron, the relative lengths are also given. Distal tubule, macula densa, proximal tubule, cortex connecting tubule, Bowman's capsule, cortical collecting tubule, medulla, then medullary collecting tubule, collecting duct, loop of Henle, thick segment of ascending limb, thin segment of ascending limb and descending limb. These are the major portions. Then in each kidney there are about 250 of very large collecting ducts, each of which collects urine from about 4,000 nephrons. Regional difference between nephron structure, cortical and juxtamedullary nephrons. Although each nephron has all the components described earlier, there are some differences depending on how deep the nephron lies within the kidney mass. Those nephrons that have glomeruli located in the outer cortex are called cortical nephrons and have short loops of Henle that penetrate only a short distance into the medulla. About 20 to 30% of the nephrons have glomeruli that lie deep in the renal cortex. Near the medulla, and are called juxtamedullary nephrons. These nephrons have long loops of Henle that dip deeply into the medulla, in some cases all the way to the tips of the renal papillae. The vascular structures supplying the juxtamedullary nephrons also differ from those supplying the cortical nephrons. For the cortical nephrons, the entire tubular system is surrounded by an extensive network of peritubular capillaries. For the juxtamedullary nephrons, long efferent arterioles extend from the glomeruli down into the outer medulla and then divide into specialized peritubular capillaries called vasa recta that extend downward into the medulla, lying side by side with the loops of Henle. Like the loop of Henle, the vasa recta return down toward the cortex and empty into the cortical veins. The specialized network of capillaries in the medulla plays an essential role in the formation of concentrated urine. Some other portions, blood vessels and tubular structures and differences between cortical and juxtamedullary nephrons are there. There will be some portions like efferent arteriole and afferent arteriole, interlobular artery vein, cortical nephron, arcuate artery vein, interlobar artery vein, collecting duct of Bellini, then thin loop of Henle, vasa recta, thick loop of Henle, juxtamedullary nephron. These are the major portions. Next topic, acid-base regulation. Regulation of hydrogen ion balance is similar in some ways to the regulation of other ions in the body. For instance, there must be a balance between the intake and production of H plus and net removal of H plus from the body to achieve homeostasis. And as is true for other ions, the kidney play a key role in regulating H plus removal from the body. However, precise control of extracellular fluid H plus concentration involves much more than simple elimination of H plus from the kidneys. Multiple acid-base buffering mechanisms involving the body's cells and lungs also are essential in maintaining normal H plus concentration in both the extracellular and intracellular fluids. So in this chapter, we consider the various mechanisms that contribute to the regulation of H plus concentration with special emphasis on control of renal H plus secretion and renal absorption, production and excretion of bicarbonate ions, HCO3 minus, on the key components of acid-base control systems in body fluids. H plus concentration is precisely regulated, and that is essential because the activities of almost all enzyme systems in the body are influenced by H plus concentration. And this topic will be dealt with the help of next video.